Okay, thank you. And thank you for the invitation. All right, so I'm going to talk about three things very quickly. I'm going to give an overview of what's happening on the Exascale Computing Initiative inside the US, where we are with various projects. I'll talk a bit about the new AI initiative that was announced by the White House last week, and also kind of all the preparation that we've been making for pushing AI into the exascale capable machines, and then give a short update on our project, our Candle project, which is building deep learning systems for cancer. So in the US, back in 2015, there was a overall government initiative created called the National Strategic Computing Initiative, NSCI. And this initiative defined roles for many agencies. And in particular, the role for the Department of Energy was to create an exascale computing capability for the country. And so the DOE's purpose in this initiative is to both create the technology and use it for its own mission, but also to make it available to the other agencies who are really building applications ranging from the Department of Defense, NSF, down to NOAA and so forth. And one of the things that's interesting in this is that the NIH is on this list of consuming agencies, and DOE around the same time created a joint initiative with the National Institute for Health to bring large-scale computing to the problem of predictive oncology, and that's one of the drivers for the cancer project that I'll mention. So inside the Exascale Computing Initiative, there are really three activities. There's a thing called the Exascale Computing Project, also known as ECP, and this is run by essentially the 6 major computing labs of the DOE. And then there's a set of activities that are acquiring developing and acquiring exascale computing systems, including the Aurora system that will go into Argonne, the Frontier system that will go into Oak Ridge, and the El Capitan system that will go into Lawrence Livermore Laboratory. In addition, as part of this initiative, there are some program offices inside the Department of Energy that are also funding applications development separate from the exascale computing project. So the ECP is the largest computing R&D program ever created inside the US as a coherent effort. It's a 7-year, $1.7 billion R&D effort. It was launched in 2016 and will run through the end of 2023, roughly. It has 6 DOE labs. You can read them here: Argonne, and Livermore, Berkeley, Oak Ridge, Sandia, and Los Alamos. And staff from pretty much all the other labs are involved in these projects. There's about 1,000 researchers that are involved over 4 focus areas. So there's work on applications, work on software development, work on hardware and architecture development, and work on kind of integration. There's over 100 teams. We just had a week-long project management or project workshop in Texas about a month ago. And it's kind of amazing to have 1,000 people all in one project. If you look at the roadmap, this is a kind of a cartoon of systems that are deployed in the US or that are planned in the US. You've probably heard about the Summit system going into Oak Ridge and the Sierra system at Livermore that are number 1 and number 2. In the US, of course, we have Titan and Mira and Theta that are at Argonne and Oak Ridge, and Sequoia and the Trinity systems. Berkeley is running a K&L system called Cori and is on track to deploy a system, another pre-exascale system called Perlmutter. At Argonne, this next year, we'll be deploying an AI testbed with Cray and Intel, but in 21, there will be 2 exascale systems deployed, one at Argonne and one at Oak Ridge, and then a little bit later, probably in late 22, for exascale system at Livermore. So by the end of 22, there should be 3 exascale capable systems running in the US. Actually, there'll be exascale systems at that scale. The ECP project also involves industry. Industry has a somewhat of an indirect coupling to it. There's an industrial council that has many companies that participate. They give advice to the board in terms of priorities, their needs in terms of high-performance computing, and so on. And this is part of coupling the kind of industrial requirements into the program, but it's a weaker coupling maybe than in some other places like Europe and Japan. The ECP applications program is targeting 6 high-level areas. I won't go through them in detail, but there's national security, predominantly around the stockpile stewardship and things like hypersonic reentry vehicles and so on. There's energy security ranging across essentially all energy domains, from solar power to wind power to combustion. The project that Jackie talked about yesterday is part of this in this combustion space. Design of small modular nuclear reactors, carbon capture and sequestration, and things like biofuel catalysis design. In economic security, this is primarily focusing on 4 areas. Additive manufacturing, so 3D printing, trying to figure out how to bring simulation to the problem of predictive materials properties in 3D printing, predicting, say, earthquake hazards, urban science, a lot of science projects ranging from cosmology to materials, a lot of earth science projects, and then healthcare, cancer and drug design, and I'll talk more about those in a minute. So there's about 25 application projects. These represent probably about $120, $150 million a year of investment. And these are very much managed as projects, so they have very specific deliverables, milestones, basically every quarter to advance the capabilities. The overall goal of these applications is to create a new capability for exascale and to demonstrate that in the early days of the machine. Much like the ways that the post-K goal has been defined as a 50 or 100x or something improvement over K machine, in the context of the US Exascale relative to machines like Titan, we've defined a 50x metric, so 20 petaflops to an exascale. All of these systems have more or less the same, or all these applications more or less the same set of challenges. So optimizing for accelerators. A lot of the application programs have not yet been fully optimized for accelerator architectures, finding more parallelism, creating more physics coupling, new mathematical approaches, new algorithms, like some of the stuff Jackie talked about yesterday, and leveraging optimized libraries. So there's an attempt at trying to make it easier for application groups by having cross-cutting themes. One of the activities in ECP, in addition to the straightforward applications development, is a concept called co-design centers. So each of these co-design centers is developing libraries or methodologies that will span more than one application. So think of this as horizontal middleware that supports more than one application, ranging from things like data compression to mesh refinement algorithms to graph algorithms or machine learning, and so on. And so this strategy tries to provide some horizontal leverage. In the exascale software activity, which is funded a little less than about $100 million a year across many of the labs, they're essentially taking the software environment that works on pre-exascale systems and advancing that and adding new capabilities, making it more dynamic, making it more coupled to accelerator-based architectures, adding more supporting compilers. And here's some examples of things. So, more investment in pushing the MPI forward, since it's the backbone of pretty much all the HPC apps, putting more investment and concepts into things like OpenMP, pushing on the compilers, a lot of performance toolkits, math libraries, and so forth. If you think about the software stack that we're standing up, it's built on a software ecosystem, which includes contributions in operating systems and so on, like the project that Pete's leading, math libraries, like the projects that Jack is leading here, programming and runtime. We've got both visualization for in situ that is embedded in applications, as well as traditional visualization methods, scalable visualization for post-processing. Did a lot of applications, co-design, and development tools, and all of this is sitting on some sense, a somewhat portable hardware interface. One of the goals is to make it easy to leverage in applications the development of these new advancement of the packages. And so there is a concept of building software development kits, or this XSDK effort. This is the kind of a conceptual model of the one for math. So the idea here is that you have a set of interfaces, and behind the scenes, there's the appropriate machinery for linking to whatever package is necessary to support those interfaces. So, for example, if you were trying to link against PETSI in turn could link against multiple other components to provide capability for that PETSI library. This whole thing is designed to be integrated and managed by dependency management tools like SPAC that make it really easy to stand it up on HPC systems. All of this is open source. There's over 80 open source projects that are integrated as part of the software development, so these are available globally. Many of these have their own GitHub sites, and it's all the, in some sense, the tools that the community is quite familiar with, and these are all being integrated into a coherent ecosystem. One thing that the ECP is doing is it's standing up a continuous integration capability with each of the supercomputer centers. So we have these 6 centers that have put development machines in a kind of a DMZ zone in their network, such that on a nightly basis, tools can be built and integrated and report against a dashboard. And that capability is being stood up right now. That means that you've got work going on in the individual projects that get kind of bundled in these software development kits, and on a kind of a continuous basis, there is a building and testing process, and so we always know what state things are in, and that gets handed over to the supercomputer centers for deployment on the systems, and there's feedback that drives this loop. So that's what's happening on the software side. As a whole, ECP is going quite well. So we just had a major round of reviews, and the project is definitely on track for meeting the key performance parameters. About half of these 25 applications are in what we call the first group that will be demonstrating this kind of 50x. The other half are more new methods development that will come in the second phase. In order to manage this, we define these things we call exascale challenge problems. So these are specific problem instances around which speed up relative to previous systems will be measured. Okay, so this is a very formal process of benchmarking on systems like Titan and Summit and Cori and Theta, and then demonstrating this relative speed up on the exascale systems. And that's what the project has to do and actually to declare a success. So there's a lot of focus on continuously tracking where we are performance-wise. This software stack effort that I just mentioned goes through what we call a capability assessment, where the objectives of each of the software activities are routinely measured and provide feedback and get feedback from the HPC facilities. So this means that the software R&D is not happening in a vacuum. And then, as was previously announced, DOE has put a large amount of money, about $258 million, into a series of vendor contracts ranging across the US vendor space. And these are continuing. They resulted in exascale bids when we put out calls for proposals. And so this hardware R&D will continue. I think this is about the last year of it. And then there'll be integration across the applications and the software stack managed by that group. So that's more or less what's happening on the exascale kind of central part. At Argonne, we are continuing with our plans for deploying the Aurora System, or also known as A21. So this is a partnership with Intel and Cray. I can't say much about the details yet. Hopefully in the next month or two we'll have a big announcement about this. But I can say that the machine is being designed to support 3 types of computing. So traditional large-scale simulation applications that we've always been running. but also data-intensive applications that come from kind of science pipelines. And then the third is deep learning and this kind of AI for science direction that we're moving. So if we were looking at kind of the kinds of things that sit in each of these bins, the traditional simulation applications are things that we have a relative a lot of experience with, material simulation, cosmology, molecular dynamics, and so forth. Big data applications, these data streaming applications, are mostly coming from things like large-scale instruments, light sources, high-energy physics instruments, telescopes, et cetera, or genome sequencers, and so on. And then an emerging, kind of an exponentially expanding class of deep learning applications. Now, if I was giving this talk kind of 15 years ago, everything more or less in red would not be on this chart. And so what's happened in the last 5 years in particular is that there's a realization of two things. First of all, quantum information science is becoming a big thing, and the US is making significant investments in that with our National Quantum Initiative. In the context of the Exascale program, this is resulting in a lot of focus on quantum computer simulations on our big hardware. So that's interesting because they can exploit the large-scale memory, and that's good. There's another thing that's happening is in neuroscience. So the Brain Initiative has resulted in a bunch of projects collecting neural imaging data and both processing that as a data problem over here in the neuroscience data analysis, but then abstracting from that neuroscience data models that could be used in, say, brain simulation across different taxa and so on. That's becoming a big thing. I won't go through all of these, but basically everything that we're doing in deep learning 5 years ago wouldn't have been on that list. Now, it's not that these stacks of applications are really completely separate. We're seeing a lot of integration of simulation and AI methods. And I won't go through all of these, but we're seeing things relating from using machine learning to steer and make decisions in simulation, embedding machine learning into simulation so that you're replacing classical kernels with machine learned functions and trading time and power for a little bit of accuracy loss, something people are looking at. Using machine learning to tune kernels, so some recent molecular dynamics codes were using machine learning to essentially tune up the force fields to be optimal for the particular molecular configuration that was being simulated, and that's a more general phenomenon that we're seeing. This idea of using things like generative networks to search large spaces to choose a subset of molecular targets and then go compute properties brings it into the space of things like materials design or drug design. And then this last one here, which is quite interesting, which is using a simulation essentially to generate ground truth that augments training data for a second model that's primarily model-driven. And we're seeing this in light sources and so on. So we see this in science, that there's a strong coupling emerging between using simulations at the largest scale and bringing in AI and machine learning methods. At Argonne, this is just a snapshot. I won't go through them, but there's lots and lots of AI targets that are springing up, ranging from cosmology to antimicrobial resistance predictions, to understanding the cloud dynamics and severe storms, to predicting properties of materials and analyzing data coming off of the advanced photon source. So this list is increasing. The center itself, our supercomputer center, has expanded its outreach framework to include, of course, exascale simulations, large-scale data analysis like that coming from the connectome programs on the brain, and deep learning such as the Candle project, which I'll talk about next.